Hi everyone, let's talk about a puzzle called queen covering. In this puzzle we have a standard 8x8 chessboard and there's a queen sitting right below the top left corner of the board. And we are focused on the 3x3 square that is in the top left corner of this board. And the question is, can you move this queen in 4 or fewer legal moves so that it covers all 9 of the squares in that 3x3 part of the board? And just so it's clear, the initially occupied square where the black dot is right now, we consider that to be covered already. And if you're wondering what I mean by covered, I mean when the queen moves, it moves in a straight line, either horizontally, vertically, or diagonally. So wherever it lands, the squares in between the original location and the final location, we consider them to be covered, and we consider the initial and final squares to also be covered. Okay, so I'm gonna count down from 5. You can pause the video if you want, and then I'll cover the solution. 5, 4, 3, 2, 1. All right, let's take a look at it, whether this is possible. The answer is that yes, it is possible. So we start at the square that is right below the top left corner. We move down 2, then we move to the top right corner in a diagonal fashion, not the top right corner of the whole grid, but we move 3 moves in that direction, and then we move 3 moves to the left, and then we go to the towards the bottom right, 2 moves. And notice how we're really thinking outside the box here, because there was nothing in the problem that said you couldn't leave the 3x3 square. And by leaving the 3x3 square, we're able to cover the entire 3x3 square. And I don't have a proof that it's impossible to not leave the square and do the same thing, but I suspect that it is impossible. And for those of you who are puzzle buffs, you might be thinking that this is very similar to a problem where you have a 3x3 grid of dots and you need to cover all the dots using straight line segments without ever your pen ever leaving the page. And you're right, this is in some sense isomorphic to that problem. Thanks for watching, and I'll see you next time.